you'll see me write this pretty often for electronegativity. It's not an official symbol for electronegativity. They use chi in the textbook, which I believe is more or less like a, almost like a percent sign. It's kind of like a crooked X, kind of like that. So it's kind of like a squiggly X. So in the textbook, they'll have things like delta chi, and that's just a difference in electronegativity. So one of the main things is that there's a trend with electronegativity. So you have the periodic table. And then, I always leave off hydrogen and helium when I draw this. But anyway, okay, so the electronegativity values increase as you go up and increase as you go toward, fluorine. So fluorine is the most electronegative, and francium is the least. So some of your homework asks you to compare some elements to see whether or not they're electronegative. No, to see whether they want you to put them in order of electronegativity. So for example, if they said put fluorine and francium in order of electronegativity from greatest to least, fluorine is greatest and francium is least. Or if you did fluorine, chlorine, and bromine, and you had to put those in order from greatest to least, it'd be fluorine, chlorine, and then bromine, because as you go down a column, it gets less electronegative, and as you go to the left, it gets less electronegative. The reason is, basically it is the same. So the reason is electronegativity is a tendency for something to pull electrons toward itself. And if you think about the ions that are made over here when things turn into an ion, they tend to be positive, so they're not holding on to electrons. But the things over here become negative for the most part, so they're more electronegative. And then fluorine is small, so it's even more likely to hold on to the electrons because they're so close to the nucleus. All right. Let's see. There is a, does anybody need a second on this page? Oh, okay. Helene needs a second. All right. So there's a figure. It's called. I don't know what it's called. It's figure 4.5 in the textbook, and you'll need this as you go through the homework. There is a question on the electronegativity difference and how to rate something, whether or not it's covalent or nonpolar covalent, polar covalent, or ionic. There's also one that's called purely covalent. The figure, which is figure 4, you're good? Okay. Figure 4.5 in the textbook is basically a periodic table, and it's got a lot of numbers on it. For example, fluorine has the number 4.0, and hydrogen has the number 2.1. So if we want, oh yeah, you don't have to memorize the electronegativity numbers. Most of the time, I mean, in the homework, it's not going to give you the numbers because it expects you're just going to look them up. But on the exam, it gives you the numbers because nobody's going to memorize all those. Okay, I say nobody. There's got to be one guy that memorized them, but most people don't memorize all those. So if you want to know the electronegativity difference, here's the formula for that. All right, so that seems a little crazy, but you'll have two elements. One will have a larger, I know it's awesome, isn't it? So one will have a larger electronegativity, and one will have a smaller one. And when you subtract them, you want to subtract the small one from the big one so that you get a positive number. So in this case, we get 1.9 as the electronegativity difference. And so we have to kind of rank that. And when you look at this, you'll find actually if you look in the homework section on D2L under exam 2, you'll find a little section that is called like electronegativity chart from book by Tro. Those are just two different ways you can look at the electronegativity. One is a chart, and then one is more of a number line. So, and they have some examples on there. Those are in the textbooks that we used before, but now we got this one. Can you hear me better now? You're okay? All right. So if you're looking at 0 to 4, we just call this covalent. And we call between 0.4 and 2 polar covalent. And anything beyond 2 is ionic. So it actually goes like 0 to 3.9, 4 to 1.9, and 2 and on. Correct. And there's really only two numbers you have to remember. You just have to remember 0.4 and 2. And then it goes covalent, which this would be more like non-polar covalent.
3.9.
Polar covalent and ionic. And if you get something with a 0 value, that's called purely covalent. Or pure covalent. So in figure, what is it in the textbook? It's like figure 4.5. It gives you all the values. So that's where I got 4 and the 2.1. Ionic is after 2, correct. It's purely covalent only for bonds. There is like one other option, I think, when you subtract the 2, that you get purely covalent. Sure, no problem. Let me look and see if I can find that example. Let's see, there are 2 on there that have the same electronegativity value. Okay. So for example, there's silicon and germanium, and they're in a column like this. So germanium is just below silicon. This is one of those exceptions where with the electronegativity trend, it tends to be a trend, but it's not exact every single time. And they both have electronegativity values of 1.8. So if you subtracted those, you get 0. So that would cause them to be purely covalent. But yes, if you had something like O2, that would be oxygen's electronegativity minus oxygen's electronegativity, and that's going to give you 0. Or if you had H2, anything connected to itself is going to be pure covalent because it is sharing an electron, but sharing it equally. All right, anybody need a second on this still? Yes, that's the electronegativity difference. So how do we know 1.8? All right, so if you go to your textbook and you open your textbook to section 4.2 and scroll down, there is, or flip, depending on what kind of book you have, look for figure 4.5. That is a periodic table, and on that periodic table they give you electronegativity values instead of things like atomic numbers and stuff. Oh, it's 0.4 to 2. Oh, you mean down here. You know, I think it's because I'm an idiot a little bit. It should be 0.39. Thanks for pointing that out. And then 0.4 to 1.9. Yeah, it shouldn't go 0 to 3.9. That doesn't make any sense. Yes, you'll get the numbers on there. Correct, they would be purely covalent. All right. All right, I'm assuming everybody's done with this slide? Not slide, but this page. Okay. All right. Cool. All right. So then you also have things like this that they went over in the book. It's a way to denote electronegative or polar bonds. A polar bond is something where the electrons are more attracted to one thing than the other. So a polar bond would be something that's polar covalent. So the electronegativity difference would be between 0.4 and 1.9. So for this one, fluorine is 4, hydrogen is 2.1, so when we subtract them, we get a polar covalent bond. And then we have these arrows to draw. So what end do you think the plus part of the arrow goes on? The part with more electrons or the part with less electrons? Less, correct. And which one has less electrons? The one that's less electronegative or the one that's more electronegative? Less. Yeah, correct, less. So the one that's more electronegative will pull electrons toward it, so it gets the arrow end of the arrow. And the one that's less electronegative gets the plus sign. So this one has an electronegativity of 4.0 from that chart, and from that chart it shows you that this is 2.1. Now there's another way that they show it, and that would be with a delta sign. This is also a delta sign. This is a different kind. One is uppercase and one is lowercase. I think the one I'm drawing now is uppercase. I don't know. I should probably look into that. There we go. The curly one's lowercase. Okay, thank you. Now I know. Okay, so you do delta plus on the one that's less electronegative and delta minus on the one that's more electronegative. So that's another way to draw that out. Linus Pauling was the one that described electronegativity, or he explained why things can make covalent bonds by talking about electronegativity. Oh, okay, so things that are polar have a dipole. And a dipole is just a difference in electronegativity. So they give you a good example in the book. It's like a battery. So a battery will have a plus and a minus. And then if you look here, a polar bond will also have a plus side and a minus side. So a dipole is just basically opposite charges that are separated by a distance. I think of what else. pretty much all that this section goes over. How can you determine whether or not one is positive or negative? So what you do in that case is you're looking at the electronegativity values that you get from the chart, and you're comparing them. So one is going to be larger. Yeah, we can do that. One is going to be larger, and one is going to be smaller. The one that's larger is more electronegative, so it's going to get the negative sign. The one that's got the small number is going to be less electronegative, so it's going to get the plus sign. Yes, unless you're talking about a cation. A cation is technically positive, but when you have a polar bond, those aren't ions. They're just kind of drawing the electron one direction, but they're still being shared. They're being shared more like this. So let me change colors. So the electron is kind of hanging around fluorine, and then hydrogen says, hey, that's my electron. And fluorine says, okay, you can have it in a minute. It's kind of like children, and one of them's a little greedy, but they really don't want to get in trouble with their parents, so occasionally they'll let the little one have it for a few minutes. So that is a polar bond there. So, and of course, this is what I drew there is more like using the Bohr model. There are a bunch of different models. So let's take a look at the homework. So let me go. I think these are going to be in different order for everybody. So anybody need a second on this page? No, everybody's good? Oh, Chuba needs a second. Okay. Just put in there when you get done, Chuba, so that I know, and then I'll move on to the next one. So if you want, you can go ahead and pull up your homework, and we'll just kind of, you're done? Okay. And we'll just kind of go through it. They are probably going to be in different order, and they may not be the same questions, but we're just going to kind of go through how to solve them. Also, if you're working in a study group with your homework, it is okay if you if you help each other to some degree. You can't help somebody else do their homework. So for example, let's say I have a question, and my question is 3 minus 2 equals what, right? And I don't have any idea how to figure that out. Then I could ask a friend, I could show a friend that that's my question, and I could say, I have no idea how to figure that out. And my friend couldn't do this problem, but they could show me something like 4 minus 1, right? And then showing me how to do this one, I could figure out how to do this one on my own. All right, so that is perfectly okay. Because a couple of people, I emailed yesterday that you're not supposed to help other people do their homework. I don't mind if you study together, and it's perfectly okay if you're working on your homework together, but not doing somebody else's work and not having somebody else do yours for you. So you want to show them how to do a similar problem, not the exact same one. However, if you're an SI, it is okay to help them do the one that they've got, just to kind of give them an example. All right. So the first question that I see asks about polar bonds. Which one forms the most polar bonds? There are 2 ways to do this. One way is to use the electronegativity trend. Let's say I had like hydrogen and fluorine and carbon and oxygen, and I want to know which one is more electronegative. The first one is I can use the table or the periodic table in figure 4.5 in section 4.2, and that gives me numbers, and I can subtract the numbers, and then I can categorize them on the line, and whichever has the bigger number is the bigger electronegativity difference. The other one is if they have a really big distance on the periodic table. For example, fluorine is over here and hydrogen is over here, compared to oxygen being here and carbon being here. The ones that are far apart are more electronegative, or have a greater electronegativity difference. All right. The other one would be to go to section 4.2 and look at table 4.5 and do like we did a second ago, like fluorine I think was 4.0 and hydrogen was 2.1, and we subtracted them and then we categorized them. Based on where they landed on this number line. And so they landed in here, so that was polar covalent. And then you could do the same thing here and subtract carbon and oxygen and see where it landed. Let's say fluorine lands here, or hydrogen fluoride lands here, and then carbon monoxide lands here. This one is more electronegative or has a larger electronegativity difference. Does that make sense? Yeah? Okay. And then there's a question that asks, you to identify an ionic bond. And so for an ionic bond, you just want to remember that it's anything from 2 and up, or if you see a metal and a non-metal. So the larger charge separation, the larger electronegativity. No, that is a good question though. So what electronegativity is you have some electrons. All right, so the dots are electrons and that line is representative of 2 electrons. So fluorine is going to tend to pull all of the electrons toward it. The more pull it has, the greater the electronegativity difference between hydrogen and fluorine. The biggest distance apart on the periodic table, the larger the electronegativity difference is. Because remember, the trend is that this is small and this is big. No, backwards. This is large. And this is small. So if they're very far apart, they tend to have a larger electronegativity difference. Does that make sense, Amelia? Okay. You're welcome. All right, and so another way to do the question of whether or not something is ionic is to take a look at their electronegativity values, subtract them, and see if the answer is 2 or more. For example, they have one set on here that is boron and hydrogen. So to look at boron and hydrogen, anybody need a second on this page? No? Okay. All right. All right, so we got boron and we got hydrogen. So looking down the periodic table, I see that boron is 2.0 and hydrogen is 2.1. So take the big number, subtract the little number, and I get 0.1. So that's not a very big electronegativity difference. It's not ionic because to be ionic, this number would have to be 2 or more. So let's take a look at the difference between sodium and chlorine. Chlorine is 3.0, and sodium is 0.9. So then we have 3.0 minus 0.9, and that gives you 2.1. And this is 2 and up, so that makes it ionic. You can also tell this is ionic because there's a metal and a non-metal. All right, so let's see what other questions it asks in the homework. There's one that asks you to arrange things in order of increasing electronegativity. There are 2 ways to do that. One is to use the trend, which is electronegativity increases this way and this way. And the other one is to go to figure 4.5 and look at the numbers and see which one is greater and which one is smaller. Lowest energetic. Not sure what you mean about energetic. Okay, so the lowest values on the electronegativity chart. Yes, that is correct. Yeah, let me take a look at the ones that they've got there. Okay. Yeah, I would say that you can assume, for now, I would think that this would be appropriate, that noble gases are not electronegative. The reason they're not electronegative is because they're not going to pull electrons. Okay, yeah, that makes sense. They're not going to pull electrons toward it from some other atom because they've already got a full shell of electrons. And having a full shell of electrons, they're not interested in somebody else's electrons. Sure. All right, so one way to see if a pair is ionic is if there's a metal and a non-metal, that's ionic. The other one is to take their electronegativity values, which would be from figure 4.5, and subtract them. And if you have something that's greater than or equal to 2, then it's ionic. Yes, I would say it is only electronegative up until group 17. I'm going to take a look at that after I'm finished teaching today, just to make sure that I'm right and that I'm not telling the whole class something wrong, because I'm definitely not perfect, and I have done that before, and I don't want to do that. So if I turns out that I'm wrong about the noble gases and they do have an electronegativity value, I will let you guys know. I will email the class. Ionization is a little bit different. The ionization energy has the same trend. So ionization energy has the exact same trend here as electronegativity, because they have to deal with pulling electrons toward themselves. I don't think that you can. Let me look. No. So yes, actually. If you click on the periodic table where it says See Periodic Table, and click where it says, no, I would say no. This makes it hard to see. Okay, so if you click on electronegativity, it'll give you the trend of electronegativity, but it's not going to give you the numbers. There are a couple ways. You can go to section 4.2 and look at 4.5 to find the electronegativities. The other one is you can actually just Google electronegativity periodic table, and then you'll find that. two nonmetals could be considered ionic if over two. Yes. Let me think of an example where they would be ionic. Acids tend to be classified as ionic when you're looking at electronegativity. Not all acids, but a lot of them. So, for example, let's take a look at, well, trying to look. You know, I'm looking, I don't see, well, okay. Fluorine and boron. Fluorine is 4.0 and boron is 2.0. So technically they're right there on the edge. And boron is a metalloid, but it's not really a nonmetal. So the nonmetals that we have are carbon, and that's 2.1. Nitrogen is 3.0. Phosphorus is 2.1. Sulfur is 2.5. Selenium is 2.4. Fluorine is 4.0. Chlorine is 3.0. Bromine is 2.8. Iodine is 2.5. And hydrogen is 2.1. So looking at that, I don't see a difference of 2 or more in any of the nonmetals. Does anybody else see a difference of 2 or more there? I don't. So I would say if you have 2 nonmetals, they're not ionic. And if you have 2, like a metal and a nonmetal, then they are. A chart like this, all of the values will be given on the exam. They won't give you a chart, but what they will give you is they'll say something like, the electronegativity of fluorine is 4.0. The electronegativity of boron is 2.0. What is their electronegativity difference? Or are these two ionic? Or something like that. But they'll give you the numbers. All right, let's see what else they ask. You're welcome. Yes, that is correct, Chris. That's why it's between 0 and 2. All right. So they give you one where you put them in order of greatest to least electronegativity. They give you another one where you do greatest to least electronegativity. So much noise in my house today. And then they have you calculate the electronegativity difference between 2 atoms, just like we did here. And then they want you to classify it as ionic, polar covalent, or nonpolar covalent. So between 0 to 3, I'm about to do it again, 0.39 is nonpolar. Between 0.4 to 1.9 is polar. And 2.0 and onward is ionic. All right. And then the last question they have is probably going to be a little confusing if you don't remember Lewis structures. But let me kind of give you an understanding of all you need to know about the Lewis structures there. Anybody need a second on this page? Nope. Okay. All right. So let's see. Let's do carbon dioxide. All right, if I'm going to label a bond with partial charges, then in this case, I'm looking at two identical bonds. They're both carbon to oxygen. The one that has the lowest electronegativity value gets the partial positive. The one that has the highest gets the partial negative. So in this case, carbon gets the partial positive and oxygen gets the partial negative. I'll just give you one of the examples that I'm seeing here on the homework. All right, and it asks you to label the most electronegative bond and put the partial positive and partial negative there. So you have some carbon-hydrogen bonds, a carbon-oxygen bond, and an oxygen-hydrogen bond. So you would need to get the electronegativity values for oxygen, hydrogen, and carbon. So oxygen is 3.5. Oh, shoot. Let me draw that again. Sorry. Wrong button. Okay. So oxygen is 3.5. Hydrogen is 2.1. Carbon is 2.5. And those are the only ones that we have. So the carbon-hydrogen bond would be 2.1 minus, no, 2.5 minus 2.1, which is 0.4. They consider carbon-hydrogen bonds nonpolar. I know they hit kind of right there on the 0.4, but they consider them nonpolar. Between carbon and oxygen, you have 3.5 minus 2.5, and that gives you 1.0. And then the last one is between oxygen and hydrogen. Oxygen is 3.5 and hydrogen is 2.1. All right, so those are the electronegativity differences. And so I just want to look for the one that's biggest. And 1.4 is biggest. And that was between oxygen and hydrogen. So now I just need to label them with a partial positive and partial negative. So oxygen's more electronegative because it's 3.5, so it gets the partial negative sign. Hydrogen has the lower electronegativity, so it gets the partial positive sign. And if you had to label it with an arrow, the arrow would look like this. All right, any questions on that? No? All right, well, that's all I've got for you guys today. It's a nice light day, so that's good. And we have 2 minutes to spare. All right, you're welcome. You guys have a good afternoon, and I will either see you in office hours if you need me, or on Friday. I don't think that you're going to fail. I think you should just keep trying until you get closer to the drop date, and then see how things are going to be. So it might get better. So. Okay, so for one of the homework, one problem asked for the ratio of the electronegativities for the two different elements. That would just be, so if I want the ratio between carbon and hydrogen, carbon's electronegativity is 2.5 and hydrogen's is 2.1. So this is the ratio, and you could just put it in a you could either give it to them like this. It depends on what format they wanted it. You could do 2.5 to 2.1, or you could do it in fraction form, or you could put it in the put it in your calculator and just get a number from dividing. You're welcome.